Let's get started. As you're all aware, we have an exam tomorrow night, and my goal today is to help you see just how easy this is. Okay? This exam, the second exam, has more giggling than any other exam. And the giggling is just from people who have seen that there is only one dynamics problem. We draw a free body diagram and then we use Newton's second law twice. I got to tell you, I wrote the test yesterday and I wrote the solution key, and I was just dead bored. And I just kept on writing, F net equals MA, F net equals MA, F net equals, oh man, it's got to be something better. That's all there is. That's all there is. Now, the problem is, some of you aren't giggling. You're not giggling because you don't know how to draw a free body diagram yet, and the time's short. You're not giggling because you're not really sure how to use Newton's second law. And if you do those two things, you'd be giggling. So let's get you giggling, okay? Let's look at this homework problem that you voted off the island. The first part of this asked about the motion of block C. Well, you know from the tutorial, you know that with more mass on this side than that side of an Atwood's machine, that things are going to go this way, so that C is going to have an acceleration down and A is going to have an acceleration up. And I know this is not asked for, but I know that the acceleration of A is equal to the acceleration of C. Now, if I write those as vectors, I need a minus sign there, because they're the same magnitude but in opposite directions. Or I could write that as the acceleration of A magnitude is equal to the acceleration of C magnitude. And that's because they're moving together. When A goes up an inch, C goes down an inch. Now, the second part of this problem asks us to compare two forces. It asks us to compare the tension by string 2 on block B to the tension by string 2 on block C. Now that's an easy question to answer after that tutorial on tension. These are two ends of the same string. And we know that for a massless string, the pole has to be the same at both ends. So I could justify this on an exam by the law of massless strings. Okay? Now, it was the last part of this problem, part C, that got it voted off the island. And part C is asking you to rank the tension in string 1 to the tension in string 2. Now, this was an old exam problem, and a lot of people got the right answer, but didn't get the reasoning points, because they had all sorts of goofy reasoning. String 1 is touching more masses. No, it's not. String 1 is longer. It's Thursday. You know, just silly stuff. Now, when you're defending an answer in a dynamics problem, what you do is you draw a free body diagram and then you point intelligently at it. Let me show you how to do that. I'm comparing tension 1 to tension 2. Usually the first thing you try is to find some free body diagram that has both of those forces in it. Well, that would be a free body diagram for B. Well, I've got a weight force for B. And let's say that we know that all the blocks are identical. Let's say the weight of each block is 50 newtons. I just made that up. Okay? And then I've got two forces besides the weight. I've got string 2 pulling down and string 1 pulling up. And what do I know about the motion of B? What should this diagram scream? Down. The acceleration of B is down. Now that's a problem. If the acceleration of B were up, I could easily say that T1 is greater than T2. But with the acceleration down, I can't say anything. This is like saying, me and my brother can beat you up. That's fine. Okay, does that tell you how a fair fight between you and me would go? No. I mean, these two forces have to be bigger than that one. That doesn't help me. Now in a dynamics problem, I draw a free body diagram for everything that has mass. So let's draw a free body diagram for A. It has a weight force that is 50 newtons, if that's 50 newtons. And the only other force acting on it is a tension force by string 1. And I know that that has to be greater than 50 newtons. Why? Because the acceleration of A is up. This diagram has to scream that acceleration. Now if I draw a free body diagram for C, I have a weight force, again, equal to 50 newtons. The only thing acting on C besides the weight is the tension in string 2, and that's got to be less than 50 newtons. Again, because this diagram has to scream down. Now, if tension 1 is bigger than the weight of one block, and tension 2 is smaller than the weight of one block, tension 1 is greater than tension 2, and I would get full credit for that argument. Check that your neighbor got that right, otherwise you know what to do. Okay. I said there was only one dynamics problem. This is it. Okay. Now, granted, drawing the free body diagram is often the challenging part, and here I've done it for you. But given this free body diagram, and given the fact that the mass is 24 kilograms, and the acceleration is 6 meters per second to the right, if I asked you, how big is F3, could you do it? With your clicker, tell me what F3 is. Okay. Get your vote in. Good. The answer is C. That means you're on the right path here. Every time I draw a free body diagram, I get to write Newton's second law twice. Once in the y direction, and once in the x direction. Now, since I'm looking for F3, I'm interested in the y direction. And in the y direction, there's no acceleration. Now, this is the part that some of you are missing. How to use this equation. You expand out F net by writing all the forces in the y direction. But you have to add them up as vectors. I've got 630 newtons, and it's up, so it's positive. I have 140 newtons, and it's up, so it's positive. I have 240 newtons, and it's down, so I add it as a negative. And then I have F3, which is down, so I add it as a negative. That's got to equal, since there's no acceleration, 0. And when I solve that for F3, I get 530, so C is the correct answer. Now let's do it for F5. Okay, use the F net equals ma in the x direction. Okay, get your vote in. Good, the answer is B, but we're not as sure as we were before. Okay, let's do it together. When I expand out F net in the x direction, I just add up all the horizontal forces, but I add them as vectors. I have to be careful with the sign. So here I have 890 newtons to the right, so it's positive. I have 710 newtons to the right, so it's positive. I have 420 newtons to the left, so it's negative. I have F5, it's to the left, so it's negative. That has to equal the mass of 24 kilograms times the acceleration, which is to the right, so it's positive, of 6 meters per second every second. Okay? That tells me that F5 is going to be, this is 1600 minus 420 minus 144. And that's going to give me 1036. So the answer is B. Okay? It's just that easy. Giggle. Everyone, giggle. Okay. Good. Okay. Now, last day, we didn't have time to finish this problem. Let's finish it now. Let me remind you what the free body diagrams for A and B look like. B had just a weight force and a tension force, and this diagram had to screen 0 because we were told that A was moving up the frictionless ramp at constant velocity. Well, that means that B is descending at constant velocity. Our free body diagram for A, we had a weight force that we were told was 50 newtons. We then had a normal force by the ramp, and we had a tension force by the string. There was no friction, it's a frictionless ramp. Now if we line up our coordinate system, with our ramp, all the forces are lined up with our coordinate system except for the weight. It's always the weight. Now, I've had a lot of people come into my office with free body diagrams, and more often than not, they've broken this up incorrectly. Now, if you break this up incorrectly, you're dead in the water. So let's do it the right way. Look in the direction of the normal force, go the other way until you can make a 90-degree turn. There's the 90 degrees right there to get to the end of the vector. This is going to be the y part of the weight, that's going to be the x part of the weight. If you do it that way, this angle here is going to be the same as the angle of the hill. Now, if this is 50 and this is a 3, 4, 5 triangle, 3, 4, 5, this has to be 30, this has to be 40, 30, 40, 50. I throw away the original and I use the parts. If A is moving at 0 acceleration, constant velocity, this diagram has to be balanced in both the y and the x direction. In the y direction, what I'm calling y, this has to balance that. It has to be 40 newtons. In the x direction, what I'm calling the x direction, this has to balance that. It has to be 30 newtons. Because this is the other end of the massless string, by the law of massless strings, this is also 30 newtons. And that makes this 30 newtons, which means the mass of B is 3 kilograms. Now clearly the mass of A is 5 kilograms. Now when this was on an exam, some of the students were troubled that a 3 kilogram block could pull a 5 kilogram block up the ramp. Well, I have here a cart whose mass is 502 grams. If I take 100 grams, well, this is 1/5 the mass of that. And yet it doesn't bring it up at constant speed, it speeds it up. Okay? This weight doesn't have to cancel out the weight to go at constant speed. It just has to balance this part of the weight, the x part of the weight. Now what that means is that if I have a horizontal track or a frictionless table with a pulley, there is no horizontal part of the weight. So that means I could have the Queen Mary, the great big huge ship, on this frictionless table, and if I hung just a little teaspoon from the captain's table over here, it would accelerate the Queen Mary if it's a truly frictionless table. There's no friction to hold it back. There's a net force this way. It's going to accelerate. Okay? Now, in this problem, the part we didn't get to was, as this thing is going up at constant speed, a hand stops it and then lets go. And the question is, what is going to happen to the block A? After the hand lets go, will the block move up the ramp? Will it stay put? Or will it move down the ramp? With your clicker, tell me what you think will happen. Okay, last call. Okay, move up the ramp is what one? Well, the answer is B, it will stay put. This diagram is balanced. When the hand stops block A, it stops it by putting a retarding force here, force by the hand, to slow it down to a halt. But when the hand is removed, I go back to the exact same free body diagram that I had before. A diagram which is balanced that screams acceleration 0. Now acceleration 0 means whatever velocity you got, keep it. If your velocity is 5 meters per second up the ramp, keep that. Okay? If it's 0 meters per second up the ramp, you keep that too. Okay? And so it turns out that with 50 newtons, I can get this thing to go at a constant velocity, pretty much a constant velocity. Okay? And if I stop it and then let go, it just stays there. It has 0 acceleration and 0 initial velocity. It keeps that 0 velocity. Check that your neighbor's okay with that. The answer is B. Stays put. Okay, questions on that problem? You're going to have a problem on your test involving strings and ramps. Okay? Let's take out this this gauntlet problem. I trust that you've all tried to work this in your meantime. Does anyone need another copy of this? Turn that down there. Anyone on this row? Okay, anyone over here? I got parts A and B correct, so let's do that together. I have 3 blocks, C, B, and B, and we're told that A is a small block, that B has twice its mass, and C has 3 times the mass of A. Now, the table is going to push up, canceling the weight force in every case. Now let's do the more challenging forces. I start with the simplest free body diagram, the thing that touches the fewest other things. That's block C. And the only thing touching it besides the table is B, and it pushes with a normal force. Now there's no friction between the blocks and the table. There's no friction required between A, B, and C for them to push on each other. So that's our diagram. Now I go to B. If B is pushing to the right on C, then C is pushing back just as hard. on B. And I would use tick marks to indicate that those are third law companions. Now the only other thing touching B is A, and it's pushing with a normal force. And I drew this bigger than this because if I look at this diagram here, for C, it's screaming to the right. If I'm pushing on these blocks on a frictionless table, that's going to cause all of this, A, B, and C, to accelerate to the right. And so that means this diagram must also scream to the right. Now I do my diagram for A. If A pushes to the right on B, then B pushes just as hard back on A. I put 2 tick marks there, 2 tick marks there, and then finally the hand pushes on A. And those are my free body diagrams. Now part B asks us to identify any third law companions. Well, we've done that. That was easy. We actually used third law to draw our free body diagrams. Now part C of this gauntlet, where people started falling off the bus, asks us to rank the net force on A, B, and C. Now folks, when you're ranking net forces, don't go to the free body diagrams. The net force is not on your free body diagrams. It's not a real force. The net force is the vector sum of all the real forces. What you should use instead is Newton's second law. F net equals ma. And ask yourself what's the same and what's different. Well, if I'm looking for the net force on A, this is the mass of A and the acceleration of A. Well, B has the same acceleration. They're moving together. But B has twice the mass. So it's going to have twice the net force. Likewise, C has the same acceleration as B and A. They're moving together. But C has 3 times the mass of A, and so it's going to have 3 times the net force by Newton's second law. Now, does that make sense? Okay, you just got through half the gauntlet. Now this isn't on the gauntlet, but this is something that I think you should know. If I were to tell you that this force here, the normal by B on C, was 15 newtons, could you tell me how many newtons each of the other horizontal forces was? Don't worry about the vertical forces, just the horizontal forces. Okay? With your neighbor, find the rest of those forces. How many newtons are they? Okay, let's do it together. The key is recognizing what the net force is on each of these objects. If I look at block C, this cancels that, and the net force is this only single horizontal force. So that means that the net force on C is 15 newtons to the right. Now I said the net force on A was 1/3 the net force on C. So that means that this diagram has to scream to the right by 5 newtons. That's the F net on A. Now the F net on B is twice the F net on A, So this diagram has to screen to the right by 10 newtons. That's the F net on B. So let's make it so. If that's 15 newtons, by third law, this is 15 newtons. They're third law companions. This diagram has to screen to the right by 10 newtons. So this force has to be 25 newtons. 25 minus 15 is 10 to the right. If this force is 25, so is this, by Newton's third law. This diagram has to screen to the right by 5, so the hand is pushing with 30 newtons. Okay, it's that easy. Check that your neighbor understands that, please. Okay, now it gets challenging. We replace block B with a block D that is much, much lighter, has less mass. And we push with exactly the same push that we had before. And the question asks us, the next question, asks us about the acceleration of this system compared to the acceleration of that system. Now, twice in your tutorial, you did something that simplified the problem. You lumped things together in a system if they were moving together. And that makes your free body diagram simpler. If we lump all of me together as a unit, then we don't have to worry about the force by my spleen on my liver or my liver on my spleen. Those are internal forces, okay? Only external forces go on your free body diagram. So if I lump A, B, and C all as one unit, the only things that act on A, B, and C are the earth pulling down, the hand pushing to the right, and the table pushing up. These internal forces of B on C and C on B and A on B and B on A, they don't enter. Now if I do the same thing for A, D, and C, you'll see that the mass is smaller, so the weight is smaller. The table is pushing less. But the net force is the force by the hand in magnitude. The up cancels the down in both cases. So both of these diagrams have exactly the same net force, namely the normal by the hand. However, the system on the right has less mass, and hence to make that equation equal, I have to have a bigger acceleration. If my acceleration initially was 3 meters per second, it's now got to be something bigger than 3. Bigger than 3. If you push the same on a Cadillac and a Volkswagen, the Volkswagen speeds up at a greater rate. Make sense? Let's go to the next part. The next part asks us about the net force on block A and block C. These are the two blocks that don't get changed. How does the net force change as we replace B with block D? Well, let's look at block C. The argument's the same for block A. If I am looking at net forces, I don't go to the free body diagram. Instead, I go to Newton's second law. And I ask myself, what stays the same? Well, does the mass of block C change when I change B for D? No, C is still the same block it was before. Its mass stays the same. But now that block C is accelerating at a greater rate. How's that going to happen? In order for that to happen, I've got to have a greater net force on C. A greater net force. The same argument can be made for block A. It has the same mass, but now it has a bigger acceleration. It must have a greater net force. Now if I look at the free body diagram for C, I can see that this has an important consequence. Since the diagram for C is very simple, the net force is just whatever's behind it pushing on it. If the net force has to be bigger when I replace B with D, that means the little block D must be pushing harder on C than the big block B was. Now this is where people fell off the bus. They said, well, B's going to push harder on C because it's bigger. Bigger things push harder. That's the kind of reasoning we don't want to use on the exam. Bigger things push harder. You know, Arnold Schwarzenegger pushes harder than Mary Lou Retton. That's a dated example. I'm sorry, that's not going to help you. Okay. We argue with free body diagrams, not with bigger pushes harder. Okay? Now, that tells us that the little block D is pushing harder on C. The last part of this gauntlet asks us to compare these two forces. Which is bigger? C pushing back on B or C pushing back on D? Well, we've already answered this question if we believe Newton's third law. I mean, we just compared these two forces, didn't we? Weren't those the forces that we just had on our free body diagram? And we said that D had to push harder on C than B pushed on C. That's where we just were. Well, by third law, this force is equal in magnitude to that force. And this force is equal in magnitude to that force. So if this one's bigger than that one, then that one has to be bigger than that one. So the biggest of the two is C pushing back on D. By third law. By third law. Check that your neighbor got all the way through the gauntlet. All the way through the gauntlet. Think of this exam tomorrow night as the Hunger Games. We're just going to see who comes out the other end there. What's that? Oh, Fnet does not increase because we're told the hand pushes the same. And that is the Fnet on the system. Yeah, is a given in this particular problem. Other questions on this problem? No? Okay. Okay. District 1 back there. Okay. You had this problem in your tutorial homework, and I fear that many of you missed the point of this problem. What you were told was that the tension in string Q was 10 newtons. And you were asked to find the tension in string P and string R. Now, what you know is that system B and system C are the same. They each have the same mass, and they're moving together as a unit. Since I'm pulling this on a frictionless table, they're all accelerating to the left. And the acceleration of B is equal to the acceleration of C. Now, those two facts tell me that the net force on B has to equal the net force on C. Well, that's how I solved the problem. Since everything's moving to the left, let's call that the positive x direction. Let's look at the net force on B. B's diagram had better be screaming to the left, right? And the net force on B is equal to the net force on C. The net force on B is going to be, I've got the tension in string Q, and it's to the left, so that's positive. I have string R pulling to the right, and since it's to the right, that'd be negative. and that is the F net on B. Now if I look at C, I only have string R pulling to the left, so that's positive. And those have to be equal to each other. Now remember, the tension in string Q is 10 newtons. So if I say that 10 newtons is equal, bring this over, and I've got 2 times the tension in string R, that means the tension in string R has to be 5 newtons. Okay? So if I look at B, I've got 10 newtons to the left and 5 newtons to the right. If I look at C, I've got 5 newtons to the left. Do those diagrams have the same screen? They do. Both of those diagrams screen by 5 newtons to the left. And that's what had to be. Now if I want to find the tension in string P, I know that this diagram has to screen to the left not by 5, but by half of 5, 2.5. Why? Because it's got half the mass, same acceleration. So if I do a free body diagram for C, where am I going to do that? For C, I've got this tension force by P, and I've got 10 newtons back. And this diagram has to screen to the left by 2.5, so that means this has to be 12.5. Does that make sense? Is that what you turned in? Oh, I hope it's what you turned in, because otherwise you lost points. Okay. Now, a while back, I gave you this problem. It's on the back of that problem on static friction. Let me see if I have any more of these. Oh, I do. Okay, who needs one? Anyone else? Anyone else down here? Okay. In this problem, there's no friction between the table and the blocks. There's plenty of friction between the blocks so that they move together as one unit. And so if I draw free body diagrams, always the first step, the free body diagram, oh my goodness, I'm sorry. The free body diagram for the upper, I have the weight of the upper, I have a normal by the, this would be by the lower on the upper, and I have a force by the hand on the upper, and I have a friction force, static friction, by the lower on the upper. If I draw a free body diagram for the lower, I have the weight of the lower. If the lower is pushing up on the upper is pushing back with a normal force. Tick mark there, tick mark there. The table is pushing up with a normal force. And then if there's a friction force back, there's a friction force to the left. Static friction by the upper on the lower. 2 tick marks there, 2 tick marks there. Those are the free body diagrams. We're asked to find the third law companions. I did. And then we're asked to compare the net forces. Well, these two blocks have the same mass. They're moving together, so they have the same acceleration. They must have the same net force. That means that this diagram has to screen to the left just as much as the other diagram. And I hope you see that that means that this has to be twice that. Okay, so if this is 20 newtons, this has to be 10 newtons, and this has to be 10 newtons. So that if this diagram screens to the left by 10, so does this one. But this is the same argument we made between B and C in the last problem. Okay, unfortunately we've run out of time. Good luck tomorrow night. May the net force be with you, people. Live long and prosper.